Hey guys, I'm going to have you open up your packet to this page in your notes, and most of this is a review, so in trying to keep this under 15 minutes so I don't have to go into 2 videos, I'm going to skip to the absolute newest stuff and maybe work back and talk about a little of this, but we've been doing so well with this indefinite integration, I think I probably don't, come on, trying to move it to the next page here. I want you to go to the page that looks like, so page ahead a little bit, and I want you to go to this page in your packet. So maybe if they can pause the video here and let you find this page. And we're going to talk about one new topic. Again, a lot of this is intuitive. If you try to memorize it, that's not a good approach. So we're going to go back up and combine 2 things we already know about. Right here, if you're given a statement like this is a statement about a derivative. Dy dx in very formal notation, so we call it a differential equation. And we even last chapter multiplied both sides by the dx, and we said we could also call that differential equation in another form, dy equals 4x dx, which is what they're telling you right here. So it says we can now integrate each side of the equation. And again, when you integrate, you undo a derivative. So what's going to be left on the left here is y plus some constant. I'm going to call it constant 1 because we're going to have 2 constants, one on the left and one on the right. And when I integrate this right-hand side, I just use my basic power rule, which is going to have it be 4x squared over 2 plus some other constant. Now you can picture subtracting this constant from this side. So minusing c1 from both sides, we'll get rid of that, or subtracting, minusing is bad grammar, sorry. Anyway, and I end up with y is equal to 2x squared, and again, a constant minus a constant is just some other arbitrary constant. So I end up with this for my value of y. The original statement, again, is called a differential equation. In a differential equation, you are given a statement about the derivative, and your goal is to solve for y. Well, I just did so. And the only deal is I've got an infinite amount of solutions for y. And graphically, I kind of want to show you what that means. Remember, this is the original function, and that's actually a parabola. And it's kind of skinny. And it's really looking like this, where c is just moving it up or down the y-axis or changing the location of that vertex. And what this was it gave us the slope of the tangent line at any point. Well, you can see it's the same slope whether I'm on this graph or this graph or this graph. That constant does not affect the value of the derivative at that point. It just shifts the original graph up and down the y-axis. So what we've got here is what's called a general solution to the differential equation. It's really an infinite number of parabolas, really, that'll all have this derivative. It doesn't matter whether it was 2x squared plus 100. It'd just be way, way up on the y-axis, but its derivative is still 4x, and the slope of the tangent line at any point is still 4x. So it says, suppose we're told a specific point, that when x is 0, y is equal to 5. Well, that's interesting because now I can get specifically exactly which one of these am I supposed to give it. And it's called a specific solution. So we're going to go find that right now. So I'm told that it goes through the point 0, 5. Well, then I'm going to go to my original general solution and I'm going to plug those values in. When x is 0, y is equal to 5. So I'd have y is equal to 2 times 0 squared plus c, and that has to equal 5. Well, then that implies that c is 5. So what I've got now is a very specific parabola. It's the one y is equal to 2x squared, and my constant would be 5. And you can see that that goes through 0, 5. So when you're asked to solve the differential equation, really what you're asked to do is work backwards by integrating or anti-differentiating and find the specific solution. So I'm going to see if I can move this a little bit. And I want to go to number 18. So I am given the derivative, and it might be in this notation too. Keep in mind it might look like that, Or maybe it looks like y prime is equal. Now that's the same stuff. You just need to know that when it says to solve it, you need to work backwards and get the original function. In this case, f of x. Because in this case, it'd be y. In this case, it'd still be y. It's all same notation for the same, different notation for the same process. So I'm going to work back. I'm going to anti-differentiate. And when I do it on the left, I end up with the original function. I'm not going to put the integral on here and say, well, I get the original one back. And then on the right, I'm going to have 3x minus 1 dx. Well, on the right, I'm just going to use my power rule and say, well, that's 3x squared over 2 minus x plus some arbitrary constant, the constant of integration. So now what I need to do is figure out, well, what is this c? Well, how do I figure that out? Again, this is a whole family of functions right here whose derivative is 3x minus 1. Well, they gave me a point on the curve. So I plug the point in and I find c. So what I get is that when I put in a 2, a 3 is supposed to come out. So 3 is supposed to equal 3 times 2 squared over 2 minus 2 plus my arbitrary constant. And when I clean this up right here, I get 6. And then this would be 4, which is going to imply that c is negative 1. Just a lot of arithmetic there. So my specific solution, going back to my general solution, would be I have solved the differential equation. I've got 3 halves x squared minus x, and then my constant specifically is negative 1. And we could do this process ad nauseum, I suppose it's a good word for it, with a whole bunch of different problems. The key to it is I'm on a PDF file and it's hard for me when I'm so used to having this Smart Notebook file. So I want to go look at number 21 next. Again, we don't need to do all of these. We'll do number 21. This one says solve the differential equation, and again, it's in F format, so I want to figure out what's f of x specifically, so that the second derivative is twice x, and it gives me a point on the first and a point on the original function. Well, we're going to start our process. We are going to integrate, anti-differentiate, to remove a derivative. All right? When I do that on the left and on the right, okay, I end up knocking out a derivative, and on the right-hand side, I get 2x squared over 2 plus c. So on the right-hand side, what I end up getting there is just x squared plus c. Well, I need to go figure out the first constant, and some books will call this c sub 1. It doesn't really matter. Constant's a constant, whether it's the first one, the second one, or the millionth one. But I'm going to go use the fact that I have a point on my derivative function. When I put a negative 5 in, a 30 comes out. So what I've got here is when I put a negative 5 in, a 30 comes out. Well, that would imply that c's got to equal, I've got a 25 here, c's got to equal 5. So back to my general solution, let's make it more specific. I know that my derivative function would be x squared plus 5. Well, how does that need to be? Well, I'm going to repeat the process again. Anti-differentiate. I'm going to, again, take the derivative of both sides. On the left, it'll leave me just the original function. And again, you could write that as f prime of x dx, and that just gives you f. Note the derivative will give me f prime. So if that's bothering you that I'm leaving the integral symbol on there, that it just undoes the derivative. And then on the left, right-hand side, when I take the integral of this side with respect to x, I'm going to get x cubed over 3 plus 5x to the first plus a second arbitrary constant. And you can again call that c if you want. And you can guess what I'm going to do. It gave me a specific point on the curve. So I'm not going to finish that one out, but I would say that it's negative 1. The value of the function is negative 1 when x is 2. So I'd say 2 cubed over 3 plus 5 times 2 plus c. And I would go solve that for c. And when I'm done, my specific solution would be x cubed over 3 plus 5x plus, and I'll tell you if you solve that for c, you actually get a negative 41/3. And that would be your original function. And that process is called solving a differential equation. So, in a what do I have here for time? I do have some time to work back, and I am going to do that for you. I want you to take and go back a page or two. Let's see if it'll allow me to hit previous. And let's revisit a couple things. First of all, let's revisit our trig functions because it's been a weekend. And generally, I will allow you with the cotangent, cosecant, and that stuff. You don't need to memorize those. What you'd probably see on the AP is just the sines, cosines, negative, etc. So I think it's easiest for us to differentiate. So remember we talked about on Friday how you can start with sine, whose derivative is cosine. The derivative of cosine is negative sine. Opposite the derivative of sine would be opposite cosine. And likewise, opposite the derivative of cosine would be sine. And this is taking the derivative going this way. When you go in reverse, or up this, you would say that you're integrating. So the integral of cosine is sine. It helps you avoid some sign errors, some sign errors, not the trig function sign. So let's go do just a couple, just to refresh our trig brain. So remember the constant multiple rule. The constant can come out front. I am to integrate sine x, right? Sine goes to negative cosine when you integrate or go up or go in reverse. So that's going to give you your negative 4 cosine x plus my arbitrary constant. All right, so let's go take maybe a look at number 22. Remember that 1 over cosine is equal to secant, and 1 over sine is equal to cosecant, and that's going to kind of help you clean some of these up. Regardless, on this one, 5 can come out front. It is a constant. And I've got 1 over cosine squared x dx. Well, 1 over cosine squared is secant squared x dx. And again, you've got to think of the derivative of what gives you secant squared. And you should remember that from our chapter 2 that was tangent. If not, you've got it written up above there. Let's do one more of these. Let's go take a look at 25. You might be wondering whether theta in this case is a constant or a variable, but remember this right here gives you your variable of integration. So you're to view theta as a variable that's changing. It's an angle that's changing, but a variable nonetheless. So I can split these up into theta squared d theta minus 2 times the integral of cosecant squared theta d theta. All right, it sounds weird to say. So I'm going to integrate these exactly as I would if it's x. I'm going to add 1 to the exponent and then divide. I've got minus 2. And then I've got the derivative of cosecant squared. And if you look above, that's negative cotangent. So it's going to cause that to go plus cotangent theta. And then I've got plus my constant. So that would be called my integral or my antiderivative. Keep in mind, again, it's a whole family of functions. The only thing this C does is it moves the entire function up or down the y-axis, even if it's a trig function. It doesn't matter whether it's sitting here or here or here. Regardless, at any point, the slope of the tangent line on all of these general solutions is the same. And again, what we just did on the other page is we found the specific solutions. So I think that's all I need to cover for you guys. Now I'm going to give you a little incentive to use the work time. I told you that section, what section are we in? 4.1, all 3 assignments are due tomorrow, but if anyone can give it to me today, I will give you some extra credit if I get the whole thing in. So you're going to be getting a worksheet. If you're already done with the 2 book assignments or close, I'd suggest you put quite a bit of effort into finishing this worksheet, turn it in, and I'll give you a few extra points, which really happens in here for extra credit for homework. So I would take advantage of the 40 minutes you have left, and you guys have a great day. We'll see you tomorrow.